have Tim DeVries talk about the recap 2 synthesis that's going on now. Tim, are you ready? And May, do you have those slides up? Or let's wait for those slides. Okay.
Yeah. Okay. I'm ready.
All right. Thanks, Tim. Here you go. Here you go.
I'm just walking up the stairs, so pardon if I get out of breath. This is just a brief summary of what we're doing with the Recap 2 project. And I should say I just copied this information from Judith Hauck and Nikki Gruber's working group document for Recap 2. So they are responsible for all the information here. So thanks to them. So yeah, next slide, please. So just to talk briefly about the objectives of Recap 2 broadly are to quantify anthropogenic greenhouse gas emissions. So this includes CO2, methane, and nitrous oxide. So there's groups for each of those gases. And to basically try to quantify using observation-based estimates changes in the carbon storage and greenhouse gas emissions by the different ecosystems, oceans versus terrestrial. And you can see the rest there. So for the ocean specifically, because we broke down into the ocean group, atmosphere group, and terrestrial group. Ocean specifically, we want to quantify the ocean carbon sources and sinks and the changes in the carbon stocks for the past 3 decades using a combination of observations and models. Look at the magnitude of the variability in the ocean carbon sink and what processes might drive that. And then also examine the biological carbon pump on a global scale and regional scale for all these as well. The analysis period for Recap 2 is going to be 1980 to 2018. So next slide, please. So just to let people know what the timeline is, quite a few people at this meeting are involved in Recap 2 too, but if you're not, just so you know what's going on. Last year, about a year ago, we had the initial All Recap 2 meeting, where we kind of laid out the scope of the project and the different authors that are in charge of the different chapters of the reports. This past February at Ocean Sciences, we had an Ocean Recap 2 meeting. Basically, by this summer, we're hoping to have all the data submitted. So all the people that are going to provide data that's going to be analyzed as part of this project are going to have submitted. And also this summer to have the initial analyses and first drafts completed. Sometime in the next year, who knows when now, based on the situation we have the second All Recap 2 meeting, and then next year around this time to have papers submitted. Next slide, please. So the data sets that we're going to use for the ocean part of this, so Recap 2, are the ocean biogeochemical models. So these would be similar to the model used for the global carbon budget that Nikki was talking about, or for the OMIP project. So these are basically hindcast models. And there's 4 different experiments that the groups can undertake. One is kind of the standard one where we have variable climate forcing from reanalyses and increasing PCO2. And then different ones to get at kind of anthropogenic versus natural CO2. So one with constant climate and constant PCO2, so kind of baseline, no variability. Another, and then the other permutations there, so constant climate increasing PCO2 or variable climate constant CO2. Then we also have data from inverse models. So these are typically going to be resolving the anthropogenic CO2 uptake by the ocean. So there's various ones there, some of which I talked about in the previous talk, like the ocean circulation inverse model. Then we have the surface ocean PCO2 products. So for example, Peter Landschutz's product, or one of Christian Rodenbeck, or Luke Greger, who I had misreferenced in the previous talk. So these are from, for example, the SOCOM project. And then we also have the ocean interior products. So bringing all these together to look at this ocean carbon sink. Next slide, please. The people that are involved with Recap 2 are as listed on slides there. So if you want to contribute data products or otherwise want to be involved with Recap 2, you can contact those people. So Nikki Gruber and Judith Hauck and Masaishi are the steering committee. And Nikki Gruber and Judith Hauck have put together kind of all the protocols for this Recap 2. For river fluxes, Laure and Pierre-René. Again, modeling protocols refer to Judith. And for data storage, Jim Orr, Nikki Gruber, and Roland Safarian. I had another slide on papers, but maybe it was cut because of time. I'm not sure. Is that slide in there, or do I have time, or should I just stop talking?
No, go ahead. You have a couple more minutes, 2 more minutes.
Okay.
You don't have
so
a slide.
Maybe
you can just
go back a couple slides. Back. Oh, yeah, there it is. So just for people's information, the kind of papers that we thought would come out of this project are outlined there. And again, if you're interested in contributing to these papers or contributing data products, we'd be more than happy to have more people come on board. You can always use more help. But we'll have a paper on kind of the global ocean carbon sink, its mean and its variability from these different methods. So myself and Rick Wanninkhof are leading that chapter with help from many, many other people. So the people in parentheses are the kind of lead authors, and of course other people are involved as well. Then we have a paper on planned on the seasonal cycle in the global ocean, talking about changes in the seasonal cycle, in particular its amplitude as we go into the future. Keith Rogers and Jörg Schwiner leading that. A paper on the biological pump and ocean carbon cycle. So Scott Denny and Stephanie Hansen are leading that. And this will deal with estimates of NPP, carbon export, the fate of carbon in the interior ocean, et cetera. And then the global coastal ocean, as we've been hearing about, this is going to be led by Agolven, Pierre-René, and Minhei Dai. Looking at the land-ocean atmosphere continuum and carbon fluxes in that zone. And then also papers dealing with regional budgets of CO2 in these different regions: Southern Ocean, Pacific, Arctic, Atlantic, and Indian Oceans. So that's just an update to let people know what's going on with Recap 2. And again, you can contact anyone involved if you want to jump in to be involved with that. That's it.
Hey, Tim, a quick question. Is there a website for Recap 2 for people to refer to as things evolve?
There is. I don't know kind of what's the state of it right now. I can kind of see what I can find and put in the chat, maybe a website or maybe a link to a Google Drive or something like that people can refer to.
Yeah, that'd be great, because clearly there's a lot of overlap in terms of the interests here.
Oh, definitely. Yeah.
Yeah.
Maybe I can just comment on that if there are no other questions right now. So there should be a web page, and we're working on that. And I'd also like to add maybe that finally all the data for the modeling protocols has come together, so that will be sent around by the end of the week. And we will make sure to reach out to the wider community to get everyone involved who would like to be involved. But we're still working on how to do the outreach.
Great.
Great, thank you, Judith. We look forward to hearing more about that. Okay, so Pedro, we're going to give up on getting Pedro connected today, and so let me just say, so that all the attendees here, going back to the point on the IPCC chapter, we are not going to discuss the IPCC chapter here because there are confidentiality issues, and only people who are signed up as reviewers and have signed the confidentiality agreement can have that discussion. So we're going to do that tomorrow on day 2. But there is, just to note to everybody, that the IPCC chapters are now open for review. So you should go sign up and read them and review. There's an ocean chapter, a carbon chapter, summary for policymaker. It's all there to be read. It's very interesting. And so, but for this meeting, we're just going to discuss the IPCC tomorrow. Okay, so then we will move on to Chris Sabine's talk about the IOC-R. Take it away, Chris.
Thank you. Can everyone hear me okay?
Yeah, we got you. We can hear you.
Great. So I've been asked to talk a little bit about the Integrated Ocean Carbon Research Group. This is a formal IOC working group that Rick Wanninkhof and I chair, and it has a number of sponsors that are shown here in this slide here. And let me just give a little bit of background on that. Next slide. Those of you that have been around for a while know that there are a number of international research programs that have ocean carbon as one piece of their mission, but it's only one aspect of a much larger mission. So there's IMBER, that's really focusing on the interior ocean. There's SOLAS, which focuses on the air-sea interactions. And there's CLIBAR, which is the climate variability. All of these obviously touch on ocean carbon, but ocean carbon's not a central component of it. Next slide. We also have the Global Carbon Project, which is obviously very focused on carbon, but is not exclusively thinking about the ocean. Next slide. And then there's the IOCCP, which is focused on ocean carbon, but it is not a research program per se. They coordinate the carbon observations, but are not really developing the science questions and the science drivers that are leading to the science directions for ocean carbon research into the future. So each of these different organizations have bits and pieces that are relevant to the ocean carbon, and they've all been, over the past multiple decades, working on different parts of the puzzle. You know, SOLAS has been focused on the air-sea interactions. IMBER has been focused more on the ocean interior and so forth. But there was a recognition, that now we really need to kind of bring all of this together and think about, all right, what are the directions that we need to go for the next decade? Next slide. So the idea of this IOC-R is to try and bring all these different research groups together to think about how do we move forward, and what's a strategy for how to advance our understanding of ocean carbon in the future. And I should note here that this is really focused on the international research programs. There are, of course, a number of national programs that are also relevant and a part of all of this. So OCB, for example, we expect to contribute. The Comfort is a EU-funded program in Europe that's also doing carbon work. So all these different pieces And the goal here is to try and coordinate all of this. Next slide. This is all packaged underneath the IOC umbrella, and the reason why IOC is really interested in this is, of course, that they are promoting the UN Decade of the Oceans that's going to be 2021 to 2030, and IOC is very much a part of that. And next slide. As part of that effort, the UN, UNESCO, IOC is supposed to develop these science action priorities. And so one aspect of that is this ocean carbon work. So we're focused on trying to develop the science action priorities within the international context for ocean carbon. But as you can see, the idea behind all of this, at least from the IOC's perspective, is to develop action outcomes, and then that will ultimately lead to contributions to societal outcomes, being the Sustainable Development Goals. So that's kind of the context under which all of this is being performed. Next slide. And so we've just started working on this. We had our first workshop in October of last year, just before we were all forced to isolate ourselves. So we snuck in under the wire there. We had 34 participants from 16 different countries, and it was just a great opportunity to kind of get together and brainstorm on, you know, where are we and where are we going and what are the major issues. As you can see from the figure here, we drew a lot of pictures of, you know, kind of how to frame this, and really tried to think about, you know, cross-cutting issues and how do we try and tie all this together. Next slide. So we came up with 4 key questions that we thought were important to address. The first one, of course, is will the ocean uptake of anthropogenic CO2 continue primarily as an abiotic process? It's been presumed that all this anthropogenic uptake is just a passive uptake of CO2 into the ocean as atmospheric CO2 increases. But of course, ocean acidification and all the various feedbacks, some of which we talked about today, particularly in the Arctic, could change the rate of ocean uptake in a way that involves biology or processes other than what we think have been the dominant processes over the past few decades. Next. So clearly, as a part of this, we want to try and understand the role of biology in the ocean carbon cycle. You know, what are the major mechanisms for moving carbon through the ocean, and how might they be changing as a result of climate change or increased CO2 or changes in buffering capacity, or all of these things. So there was a very strong message at this workshop that we need to better integrate. So of course, there's a whole community of people that have been looking at ocean biology for a long time, but the idea here is that we need to better integrate the biological measurements with the geochemistry measurements to try and better relate these two things together. Next. We need to look at the exchanges of carbon between that land-ocean continuum. We've seen that here today in the discussions and the talks that we've had so far, that the coastal zone is obviously a very dynamic region. It represents a stronger component to the global carbon cycle than one might imagine just based on the area of the coastal zone. And so we need to understand what are those contributions and how are they changing over time. And in particular, again, recognizing that there are a number of coastal programs and programs looking at the relationship between the coastal ocean and the land, we thought the niche that this group really might focus on is that connection between the coastal ocean and the open ocean, and what are those fluxes between those two regions that we need to consider in the global carbon budgets. And then the last question is, look, if you can go back, is looking at what role are humans playing in all of this? You know, obviously humans are producing the emissions of CO2 that are increasing CO2 in the atmosphere and the anthropogenic uptake. But in what other ways are humans directly or indirectly altering the ocean carbon cycle that we perhaps don't fully appreciate? Looking at lateral fluxes, looking at direct emissions of CO2 or carbon products from the coastal zone into the ocean and so forth. And so we are moving in a direction that I think much of the carbon community is moving, of recognizing that humans are an integral part of the global carbon cycle and the ocean carbon cycle, and need to be considered as one component of this integrated ocean carbon process. Okay, next slide. So there are a number of approaches that we want to look at. Of course, we wanted to first evaluate what are the opportunities and challenges, what are the gaps, what are the directions that we're going, what are the new approaches that can perhaps answer questions that we couldn't have answered even a few years ago. Next. We need to solidify and expand the network of core observations. There's a recognition at this workshop that while we have these wonderful global surveys of ocean interior carbon with the GOSHIP program, and we've got the surface observations from the underway programs, and we've got all the moorings, and we're getting BGC-Argo, that these programs, while they do exist, are kind of operating hand to mouth, and there really is not a firm funding source here that's going to sustain these critical observations. Next. We need to develop regional priorities. Next. Just going to kind of blast through these since my time is running out. We need to consider what new process studies and experiments are needed. Next. Identify new tools and approaches that can apply to these questions, right? So the Open Ocean program has generally focused on these large-scale monitoring efforts, but we want to look at this more from a research standpoint and say what process studies are needed and how can we use these new tools to try and address some of these questions. Next. Again, I've said a number of times we need to emphasize integration, and particularly looking at models and observations, trying to integrate those together. Next. We need to consider the ocean's role in climate solutions. So we're not really going to be focused on mitigation or ocean carbon storage, but that needs to be part of this portfolio of what we consider, because we've gotten to the point now where whether we want to study it or not, it's likely to happen. So it's better off that we put some science behind it. Next. And finally, we talked about how do we coordinate all of this and talk about our proposed oversight and management mechanisms for this integrated program. And I think I have one last slide, which is just a recognition that there are many different parts to all of this. There are a bunch of programs that all have pieces of it, and we anticipate that those programs will continue. We're not trying to subsume any sort of anything from these groups, but we want to try and be that mechanism that coordinates all of these. And I think that's it. Thank you.
Thank you very much, Chris. Do we have any quick questions or clarifications? I don't see any in the Q&A or in the chat. Okay, we will then go on to Judith is going to talk about the global carbon budget.
All right, thank you. So I'd like to take the opportunity, first of all, to thank everyone who is contributing to the ocean carbon sink estimate in the global carbon budget, which we put together once a year. And particularly to thank everyone who really sticks to the very strict timelines that we have. So starting from the surface PCO2 submissions to SOCAT, to the quality control in SOCAT, and then the production of the mapping of the database products, and also the modeling runs, which all come in over the summer to be then submitted in September and be published in December usually. Next slide. I would also like to take the opportunity in this talk to really make clear what it is exactly that we estimate in the global carbon budget, because I do think that's not always clear, and I do notice that from the discussions and the questions that we do get. So what we estimate in the global carbon budget is the anthropogenically perturbed ocean carbon sink. Next slide, please. So we usually think about the ocean carbon sink as one flux into the ocean, so just one error, right? But we've also heard in talks today that really it's the sum of multiple processes and much larger fluxes going into and out of the ocean. So it's really not just one flux. So let me go through the components of the fluxes that we consider to be part of the contemporary ocean carbon sink, and which of these we include in the global carbon budget. Next slide. The first component is the natural CO2 flux. And in the following, I'm going to distinguish the steady state and non-steady state fluxes. The steady state is really just the long-term mean, and the non-steady is any deviation, so temporal and spatial variability deviating from the long-term mean. Thinking of that in a pre-industrial world, the non-steady state would just be natural variability. Next slide, please. The next component is the riverine fluxes, which we've already heard about. So there is organic carbon being transported from the land via rivers to the ocean, and part of that carbon is lost again to the atmosphere, and another part is buried in the sediments. So the steady state compartment, I think we do agree on that, at least that would have been an outgassing flux from the ocean to the atmosphere. And then there's also a non-steady state component, so temporal and spatial variability to that. Next slide, please. Moving on from the pre-industrial ocean to the contemporary ocean, then there come the anthropogenic CO2 fluxes into play. So this is really just a flux mostly into the ocean, which is directly driven by the increase of CO2 in the atmosphere. And again, there's a steady state flux, and there's also a non-steady state, so spatial and temporal variability component to that. And now in the modern world, where this increase of CO2 in the atmosphere leads to climate change, all these non-steady components do include not only natural variability, but also components of climate change. Next slide, please. So what is it that we estimate in the global carbon budget? It's really the anthropogenically perturbed ocean carbon sink. So that is all the anthropogenic fluxes being directly influenced by the increase in CO2 in the atmosphere. And it's also the non-steady state fluxes of the natural carbon, because that has a contribution by anthropogenic climate change. In principle, we should include the non-steady state river fluxes, but we just don't have any data on that. How much do the river fluxes change from year to year due to anthropogenic perturbations? We don't have enough information or any information to include that on a year-to-year basis. Next slide, please. And that's one question that had been raised at Ocean Sciences and also outside of Ocean Sciences. how well does the GCB estimate agree with ocean interior data? And I would like to make the point it agrees extremely well. So the GCB estimate that we can calculate here based on the models for the period 1994 to 2007 gives a number of 2.1 plus minus 0.5 petagram carbon per year. Now, of course, I've chosen this period, next slide please, because it overlaps, or this is exactly the period. Can I get the next slide? That is exactly the period for which we have the ocean interior observations and the anthropogenic carbon estimate from Nicholas Gruber and lots of colleagues. But what Nicholas Gruber does here is the anthropogenic carbon estimate, and that's not directly comparable to the carbon budget estimate that we do in the global carbon budget. So the anthropogenic ocean carbon sink that in the Gruber et al. Paper is 2.6 plus minus 0.3 petagram carbon per year over the same period. And even these two numbers overlap within their uncertainties, but in the Gruber et al. Paper, there's also a number given for the natural CO2 outgassing in this case of 0.4 petagram carbon per year over the same period. So in order to make the two numbers comparable, the natural flux has to be subtracted from the anthropogenic flux, and then this gives a number of 2.2 plus minus 0.4. So 2.1 versus 2.2, I would say this agrees extremely well. Whether this is for the right reason or not is a different question, right? Next slide, please. And then I would like just to make a few more or less general statements on the consistency and uncertainties in the global carbon budget ocean sink estimate. So I've shown two of these figures already in my introductory slide, but I'd like to make this point again. The large discrepancy in the global ocean sink estimate between the multi-model mean and the data product mean can really be to a large extent explained by the discrepancy in the Southern Ocean. So in the North and in the tropics, the means agree pretty well, at least in the last 15 years. And the models and data products also agree on the variability in the tropics. Whereas in the Southern Ocean, there's not an agreement neither on the mean, nor on the trend, nor on the multi-year variability. And there are two possibilities for that I think would be the first and obvious ones to test. And the first is the river adjustment. So it seems to me to work pretty well in the North and in the tropics, but it does not seem to work in the South. So maybe there's just a regional distribution that we don't get right yet. And then the second point that could explain that is a potential overestimation of the CO2 uptake in the data product estimates. And this has been shown in principle by Seth Boshinsky et al. That the missing winter data in the data products really lead to a too large uptake estimate. And the last point that I would like to make here is that yes, of course, the models do have biases and drift, but we do correct for that, and we can show that the multi-model mean is really very insensitive to these biases and drifts. Regional distribution variability, that's a different story, but I do think the models get the global mean pretty well. Thank you.
Thank you, Judith. Let's see. So Judith, I had one question on your last slide. Maybe we could go back to that. So if you look at the models in your Southern Ocean there in particular, there's ones that are really strong outliers, really big sink, really small sink. Have you considered, and my understanding of the global carbon budget approach is we use these very broad IPCC AR4 estimates of what the mean sink was in the 1990s, sort of to say a model's okay or not. But have you considered using more metrics, more kind of ways to sort of reduce the size of your ensemble to give you something that is maybe less extreme?
Well, we do a lot of model evaluation now that we can mostly do in terms of the ocean PCO2 observations. And yes, we do look at that in more detail now. And also more since the last budget was published. In this special case, I think there's a high and a low outlier, so they would even cancel out, I think. But yes, of course, the divergence, I mean, the range is largest in the south. Totally agree with that.
Okay, are there other questions?
Judith, is there a way that you handle the forcing uncertainty? So, for example, one of the hindcast models may be using NSEP-NCAR and one may be using JRA. How is that accounted for here?
Well, if we would know which of the forcing is best and which is right, we would use that, but we don't, right? So what we do ask the modeling groups is to give their best estimate. And I mean, let me put it a bit provocative. I think the forcing is also a model tuning factor, right? So dependent on how you choose your forcing, you have to retune the model anyways. So I think the models are just tuned to their specific forcings to reproduce the observations as best as possible.
Maybe I should be more specific. So in terms of, for example, the uncertainty in the ocean carbon sink globally, do you break down, or do you plan to, for the next budget, break down this uncertainty into various components? One of them might be the uncertainty due to forcing. Another might be the uncertainty due to bias or spin up or whatever, which you just have said is actually quite small.
Well, I mean, I do have quantified the uncertainties to the due to the bias and drift, and that will be published soon. I hope. I don't have any way yet to quantify any uncertainty in the forcing. If you do have any, I'd be pleased to hear.
I'm just wondering, maybe for at least the models that we have, OMIP 1 and 2, where we know what the forcings are and we know that the forcings are different and they have the same structure, we could begin to develop an envelope of uncertainty associated with the atmospheric forcing. And that might be useful for this working group and perhaps moving forward. Yeah.
Judith, there was a clarification question about the use of the south on your last slide. Is that Southern Hemisphere or Southern Ocean?
These are very broad bands, so south is everything south of 30 degrees.
Thank you.
Can I ask a question?
Of course, it's only the ocean. It's only the ocean, and there's no land in it.
Yes, Ray, please go ahead.
I must be missing something, because I thought earlier we were being shown that the data-based estimates are give a weaker sync than the models. And here in the upper left, I'm getting the signs right on everything here. Looks like the data-based estimates are a greater sync. So
yeah, it's so important.
am I missing?
Yeah, it's so important to know what to compare. I think Tim was showing the data products for the contemporary sync, comparing to the anthropogenic sync from a different estimate. And so what's important here in this comparison is the river flux adjustment, right? The data products would be lower than the models without a river flux adjustment. But then it's a different definition. Then it's not the same quantity that you compare.
So,
Is the river flux adjustment really that big south of 30 south?
Yes, it's huge. It's the largest of all three regions. It's 0.4 or so, I think. And I mean, that's really a big thing also for this working group and also for the recap land ocean regions. We do use the number, the 0.78 coming from Laura Resplondi's work, but the way it's split into different regions, that uses basically just an upscaling to the regional distribution from the old Jacobson paper, I think. And also it's not totally consistent in how the south and north and tropics are defined in these estimates. So the river flux correction that we apply here is actually the estimate for south of 20, and we apply it to south of 30, but we just don't have any better number.
So the river flux adjustment, excuse me, is the 0.78 that you're using globally?
Globally, yes.
And then how do you distribute it?
I would need to check the exact numbers, but it's, I think, 0.4 in the south, because the argumentation that it's huge in the upwelling regions, right? The argument is that the organic carbon just needs a really long time to be remineralized, and the largest fluxes out of the ocean occur in the upwelling regions. And the exact numbers are in the global carbon budget paper as well. I can find them.
So in Resplan, these, I mean, maybe Lauren wants to comment, but in her paper, the 2018 paper, it's 0.03 south of 20 south, 0.38 between 20 south and 20 north, and 0.36 in the north.
Those are the lateral fluxes, and then the air sea flux would be.
That's something different.
Yeah, because the
Point.
number that you're giving is for the Jacobson number, I think. So basically, that's related to what Ray was asking me. Is that you have the rivers mostly in the north in the tropics, but then they outgas in the ocean. That carbon outgas mostly in the Southern Ocean, and for that distribution, I used Aumont et al., which ran a model for a long period of time, and track where the river, where that carbon input by the rivers was outgassing. It's in the supplementary material. I can give you the exact numbers, and Judith also.
Yeah. So where it goes in, even though the river, I guess the point is that there's not a lot of land in that region. So it's not that there's a lot of riverine carbon going into the ocean in the southern, south of 30 south, but it's that there's a lot of riverine carbon coming out based on Aumont's estimate of the transport in the ocean. So that's a key clarification, I think.
Exactly, and that's 0.38 for the numbers that I have.
Great, great. And is that, because I always think of this 0.78 as applied typically just to the global scale, but you're applying it just in these large regional bands, 30 south or so, and then the tropics and 30 north of 30 north, right?
Well, and the same globally, of course. The sum is the same globally.
Yeah, of course, yeah.
But we don't have, I mean, that's another point of something that we're really missing, I think, is a spatial map, right? Of where these fluxes occur, and also how that impacts the surface PCO2, because we also, of course, compare our models, the modeled surface PCO2 to the observed PCO2, but the observed one does include rivers and the modeled one does not.
It's a very good point. And I think also, of course, ocean models have evolved a lot since that early 2000s, I think it was, study of Aumont. And so what actually is the transport could be very different and from what was estimated there. So that's something we need to better understand. Very good point.
Absolutely.
Yeah, I mean, there's a number of assumptions that go into their model. It's a very nice study, that Aumont et al. Paper, and they do some sensitivity studies with different lifetimes for DOC, and you get different results. You know, I think there's a lot of uncertainty there. They do produce a map, by the way, in that paper showing the CO2 due only to the rivers. And you're right, Judith. It has in some places in the Southern Ocean, it has quite a big impact. It surprised me.
Yes, and I do think that this can, to some extent, explain the discrepancy in the Southern Ocean. I mean, this number is really not well constrained.
It's not well constrained, but also if you look, we've done some looking at some of the models, and there's a huge spread in the mean flux of the different ocean models as well. So yes, there's also that contribution as well. So there's many things we don't know.
Yes.
Great. Thank you, Judith. We'll have, that sparks a lot of comments, a lot of things to think about for the remainder of the conversation. All right, so next we have Nikki Lovenduski, who's going to talk about WCRP Grand Challenge on decadal prediction and OMIP.
Hello, again, everyone. Good afternoon now. So I already sort of talked about OMIP, so I thought that instead I would spend these 8 minutes talking about these other two topics. One is decadal prediction and the other is the WCRP Grand Challenge. And they are interwoven in that a subset of people who are part of the Grand Challenge are also very interested in decadal prediction of ocean carbon fluxes. So I'm going to start by describing decadal prediction efforts and then describe more broadly what that Grand Challenge is all about. And can you, I'm pressing the down arrow, can you please advance the slide? Thank you. Okay, so what is decadal prediction? Decadal prediction is a near-term forecast using an Earth system model. So coming back to this cool schematic showing the components of an Earth system model, in a decadal prediction, all of the components are typically turned on and the model is run in a fully coupled framework. However, because we are interested in making a forecast of the near term, and the near term here is defined on timescales ranging from 1 year in advance to 10 years in advance, sort of a decadal timescale that we're interested in making a forecast of, you need to account for the uncertainty in your forecast due to initialization. So you take your ocean model and you initialize it multiple times and you generate an ensemble of forecasts using that those small differences in initial states. So you're taking an Earth system model, you're sort of running it like a weather forecast model, and the initial conditions are coming from some time history of how the ocean physical circulation and biogeochemistry may have behaved. So this is not always the case for all decadal prediction systems, but for at least 2 of the ones that I'm going to talk about here today, they are using initial conditions that are coming from hindcast simulations, much like the hindcast simulations that are used for the OCMIP ocean carbon model intercomparison projects that I described earlier this morning. And the reason why this matters, can you go to the next slide, please? The reason why this matters for our working group is because when you initialize the model, you're generally initializing some state in the past to see how well your forecast model can predict what actually happened. So here's an example of how you might do that. This is the mean air to sea carbon flux in some part of the world ocean. And this is showing a time history from a single hindcast model. This is the CESM hindcast model, 1948 to 2017, and that's the black line here. So the forecasts are initialized from the hindcast state, and they're initialized over and over until you generate an ensemble. And what you want to see then is how well your ensemble mean forecast matches what actually occurred in the past. So by making a forecast of the past, if you trust how well your forecast system does, you can then use the same forecast system to make a forecast of the future. Okay, so the question that I think our working group needs to address then is whether the hindcast simulation here is actually representative of the real world, right? And so for that, we need to go back to my morning presentation to compare the hindcast model output to the observationally based products that Peter talked about first thing this morning. And so what we can do with these forecasts, these decadal forecasts, is say how predictable it's possible to be. But what we can't do very well yet is to say whether or not our predictions have any skill in the real world. Until we have observationally based products that are gap filled in a way that we completely trust. The other important point here that is perhaps relevant to our discussion maybe tomorrow is that there are people who are starting to think about using these sorts of decadal forecast systems to make predictions of how the carbon cycle might behave in the next year or 2. And that's become of particular interest because of the COVID-19 crisis and the reduction in emissions that is ongoing right now. So how will the ocean carbon cycle respond to that reduction in emissions? Could we make a reliable prediction with a forecast system such as this? Okay, next slide, please. There are a number of studies that have been published using Earth system models to make decadal predictions of carbon uptake by the ocean. This is one by Hung Mei Lee that was published in 2016, focused on the North Atlantic. Next slide, please. This is one by Roland Zafarian that uses a CNRM model framework and focuses on both ocean and land carbon uptake. Next slide, please. And this one that I contributed to Earth System Dynamics last year that is represented by the figure that I just showed you behind you using the CESM decadal prediction system. Next slide, please. Okay, so 3 more slides. These are all about the WCRP Grand Challenge. WCRP stands for the World Climate Research Program. And there are a number of WCRP Grand Challenge activities These are science working groups, essentially, that are formulated to answer what we think of as a climate community, the big questions. And one of them is the WCRP Grand Challenge on Carbon Feedbacks in the Climate System, and their research questions and the group of people who are involved with this have, I think, pretty strong overlap with our OCB working group. And so I'm just going to introduce very briefly what they're doing. Their main questions are listed on this slide. So they're interested in biological and abiological processes and how these drive and control land and ocean carbon sinks. They're very interested in carbon climate feedbacks and whether they will amplify over the 21st century. And then they're also interested in vulnerable land and ocean carbon reservoirs and how they might respond to warming climate and to extremes and to abrupt changes. Next slide, please. This is a list of the people who are part of the scientific steering group for this Grand Challenge. The two leaders are Tatiana Elina at MPI in Hamburg and Pierre Friedlingstein. And then there are several other scientific steering group members, some of whom are part of this call, or Pedro Montero, for example, who I guess is having trouble connecting. Next slide, please. And so this, although it's very small, I hope you can see it, is a list of the things that they are hoping to pursue, their research objectives. And this has been ongoing for at least 2 years, perhaps 3 years at this point. I want to draw your attention to bullet point number 2, which is describing all of the things that they're hoping to do for process understanding in the ocean. So in particular, they're interested in quantifying the strength of the Southern Ocean carbon uptake, and also to diagnose the relative role of physical and biological processes in determining the strength of the ocean carbon sink. And then finally, of interest to our group, understanding the origins of variability from seasonal to decadal of that ocean carbon sink. So that's all I have to say about that. Thanks.
Great, thank you very much, Nikki. Let's see. Do we have any questions? Anybody of the panelists want to speak up? I don't see anything in the Q&A. Nikki, what do you, when the idea of decadal prediction, how do you see it intersecting with our need to better understand observationally based products and do better efforts at gap filling and filling these underlying uncertainties in the riverine input and all these things? Like, how do we connect those two threads of work?
Well, I think in a fairly straightforward way, we could think about, for example, that time series I showed with the hindcast and the forecast. What we're basically doing right now with many of our modeling frameworks is assessing how well the coupled version of the model can predict the uncoupled version of the model. And we would like to be able to take it a step further for air sea carbon fluxes in particular, and be able to say how well the coupled version of the model can replicate actual observations, right? The time history and the spatially varying history of those observations. And I think until we have observational products that we trust everywhere, we can't necessarily do that with much confidence. No offense to the Peters out there who are generating these products. They're really great resources, but I think that's the mismatch that I hope when we start to talk about the differences between the hindcast models and the observationally based products, that we can begin to address.
Say in the name of all Peters, we forgive you.
Great. All right. Other questions or comments? Okay. Then we will keep thinking of your questions and comments as we go into talking, having two, I think we're only going to have 2 presentations now on some observing systems and projects. So Rick Wanninkhof is going to talk first, and then Nancy Williams will tell us about SOCOM and Bio-Argo.
Right. I hope you can hear me.
Yep, we got you. We can hear you.
No, I think I've got a better connection now. So let's hope to go. I'm notorious for going over time, so I decided just to keep it to 1 slide, and I'll still go over time, I can guarantee you. So cut me off when need be. First, a few comments earlier on. I think I was really appreciative of Judith's presentation about the different nomenclature, and that we are really doing a lot of comparing of apples and oranges. And I think one thing with nomenclature is that when we're talking about a inventory change based estimate, like Sabine or Nikki Gruber did, it's an inventory change. It's not a flux. We are inferring a flux from that. I think that's quite important. And another, I think, an interesting tidbit is what the observational product is, which I mentioned earlier on as well. It's what I call as the net flux, I guess, in modeling terms, a contemporary flux. And the interesting part is that we're adding this some large components to this. We have a riverine component. Then we have a possible issue of the cool skin and chemical gradient effects, which I mentioned this morning. We are treating those as invariant. And so this is one way, and they mostly are not. So that when we are trying to use the net flux to infer an anthropogenic CO2 flux, we are going to miss some variability by not including the other inputs in there. But in any case, this is sort of a long prelude to my brief description of a lot of acronyms. We are doing a lot of coordination within the observing community. And I think because we recognize there's a really need for a sustained network to deal with, I think, a lot of pressing societal and economic and also ecological issues which are on the horizon. And a lot of it is also driven by the Paris Accord, where we are having high hopes that we're going to change our emissions. And the ocean could play a significant role in either meeting or not meeting the Paris goals. And I won't go into that, but I think it's something we have to recognize when we are trying to justify our work. So in any case, I basically, this was on this slide on the right-hand side, you see a nice pyramid, which I basically came from Dorothy Bucker last week, which was for a completely different purpose, to, I think, sort of justify GCOS. But in any case, this pyramid is sort of, I think, the way that I like to think about how our observations lead to sort of the higher level and more important issues. And I'll go through the pyramid and sort of touch on the acronyms I'm supposed to explain. So at the bottom is the observations. Observations are done in a non-coordinated fashion. We recognize that in order to get global and even regional estimates, we want to be sure that we use common practices and be able to be assured that all our data is of good quality and interpretable quality. And so a effort which we've been advocating, it's been sort of a slow burn, has been SOCONET, which is a CO2 reference network, where we are trying to assemble current observations, be it from ships, be it from moorings or other platforms, and then like some of the drifters that have been out there. To basically get all these data, sort of coordinate at a observational level, to be sure that we are using common practices. And if we don't use common practices, that we have a full understanding. And also SOCONET is very much focused on measurements of a quality that we believe will be good enough to do the air sea CO2 flux determinations. And it is a fairly high bar. There's an outstanding question: how can we use lower quality data appropriately? And that's something we recognize. At a regional level, there is an effort, and it's again a way. We are very good at slicing the pie at very different ways and making it a little bit confusing, but we'll have to see what the best way is in the future. Is this effort within Europe called ICOS, which is an integrated carbon observing system. And one part of the ICOS, which both covers terrestrial, atmospheric, and ocean, is the OTC, the Ocean Thematic Center, where they're basically trying to do it's an infrastructure project. The project is just focused on infrastructure. Basically by coordinating infrastructure, they believe that we can get sustained observations done in a systematic fashion for a long period of time in order to provide products which are of great use for the higher level goals. Currently, we have the Ocean Thematic Center has an energetic new lead, Richard Sanders, who came from the Southampton Center, and he is basically looking at ways that we can sustain and fund global networks. The problem in OTC and a lot of other regional networks is there's no sustained funding mechanism, and ICOS suffers from that greatly because the funding for the observations have to come from the individual nations which don't have a structure set up to fund long-term CO2 measurements. So that's sort of at the lowest level. Then we basically have at the what is called, if you can read the small letter, mapping, data assimilation, and forecasting. We basically collate our data. So sometimes there's some confusion about what SOCAT does, but SOCAT and also GLODAP, what they do is they take the measurements from the different groups and basically collate them, homogenize them, and do a higher level quality control. This is a fairly superficial quality control. There's an expectation that the quality control is done by the investigators who submitted. I think there's some problem with that. And then we advocate best practices and also look at, we've sort of boldly, as a group, have sort of decided which we basically qualify which measurements meet certain quality criteria, and we've assigned letters to the different data sets. Being the best data sets are ±2, the data sets of less good are ±5, and then we have data which is greater than ±5. So people who want to use the SOCAT database have an opportunity to sort of pick the quality of data and, of course, the number of data that they feel is suitable for their purpose. There's a similar effort going on for ocean interior work, which is called GLODAP, which is it's very similar to SOCAT. They are starting to sort of merge that. We are sort of using common ingestion products, looking at common ways of doing a QC. And for GLODAP, we actually do adjustments to the data. SOCAT does not do adjustments. They just do a common calculation of the data sets. Then you have, and then you have above that is the efforts which you heard earlier on, which are sort of, within the SOCAT community we refer to as SOCOM, which is the mapping and modeling. And this is where this exercise, which we are, this working group that is very much, at least I view it, focused on this third level of the pyramid. And the last thing, there is, as I mentioned, there are a lot of different ways that we can slice the pie, and how do we basically develop networks. And there is currently a effort undergoing, which was called the Integrated Surface Ocean Observing System. The name obviously was not liked by everybody, and now it's called OASIS. But the idea was that this was, we as ocean community got together, ocean observation community got together in Hawaii last year, and they were encouraged to basically look at integration and big ideas. And this is something that Megan Cronin at the NOAA lab at PMEL is spearheading, is basically trying to get a surface ocean observing system, which we are trying to do for, for PCO2, but make it much, much greater, looking at heat, looking at, all other, relevant trade gases. Again, we've heard it before, this is very responsive to the decade of ocean science for sustainable development. And we are sort of pushing forward on that. There is going to be a proposal to establish a SCORE working group to do more working on that. But I expect you'll hear more about ISUS OASIS in the very near future. That's what I have.
Mute. Okay.
Okay, and then one other thing.
Okay, now I can unmute.
Okay,
Okay.
I've got to
Go
send
ahead.
you trying to be muting. I'm getting some question and answers. For some reason, I can't send my answers in the question box, but I'm taking note of them, and I'll try to reach those, personal questions, by other means. But I am seeing them, and thank you very much for your input on the previous presentation.
Yeah, I think the best way to answer the Q&A is either to go to the chat and respond to all attendees, or to, or if it's appropriate, just back to the person who asked the question, if that makes more sense. Or we can talk about them verbally.
As panelists, you can respond to questions using the Q&A, but you just can't ask questions using the Q&A. That's only for the attendees. Or you can use the chat function, which the attendees can also use.
Okay, so I must be logged in as wrong, because I was a panelist, I believe. But in any case, we will deal with that.
Okay, great. All right, so are there questions for Rick on this section? I guess I'll ask a quick question, Rick. I mean, it's, obviously we'd like to have more data, and we're concerned about the ability to continue to support the observations, the SOCAT, the data that goes into SOCAT in the context that often it's just funded by individual projects, not by some sort of larger group. But besides that issue, I mean, it seems to me that the flow is working well from observations through to the products, and that things are going well. Are there other kind of structural issues that we should be aware of, or how this, what can we do to sort of support this ongoing effort and keep it going? Or
well, I think, it is sort of that, let, everyone know, including your favorite program managers, that, data does not appear in SOCAT, just use SOCAT as an example, or GLODAP, automatically. The data comes from somewhere, and there is, this effort that Richard Sanders is leading. Mm-hmm. There is, particularly in Europe, there's a real concern that a lot of the observational networks are falling by the wayside. We are losing, some key observational lines, so it's an awareness issue. I think that's the main thing. Both SOCAT and GLODAP do not have sort of a sustained funding mechanism, and these are international efforts, which make it even more difficult because there is not really one agency that funds sort of global observation. So it's a patchwork. It very much depends on one or two heroes in each of these efforts. So it's going well. We really appreciate the feedback. It is, I think it's always important to recognize, as I mentioned, that the data comes from somewhere. We have some concerns that people do not always realize where the data comes from. So acknowledgement, and also direct, and there is a very good statement in SOCAT how to basically reference this data, particularly when you're dealing with original data sets that come from a few people. And this effort relies on an open exchange. Nobody is forced to send things to SOCAT. And if we do not have this, back and forth that people realize and attribute and involve the data gatherers, it's going to be very difficult to continue.
Thank you, Rick. Thank you. Okay, let's go on to Nancy Williams, who's going to present about Bio-Argo and SOCOM.
Okay, hi everyone. And thanks Galen and Peter for inviting me to be a part of this group. So I'm going to talk about Bio-Argo and SOCOM. And I'm not actually affiliated officially with either of these programs anymore. I did a lot of my graduate work and postdoc work as part of the SOCOM project, but I think I can mostly speak to what the work that they've been doing and kind of some of the things that are planned. Next slide. So the SOCOM project stands for Southern Ocean Carbon and Climate Observations and Modeling. And it's an effort that started in 2014 to deploy about 200 biogeochemical Argo floats into the Southern Ocean. And I think that number has gone up. I believe they were funded for a second project. And These are essentially Argo floats that have the classic sensors, temperature, salinity, pressure, but also some biogeochemical sensors, including pH. And they profile from 1,800 meters to the surface every 10 days. Some of them are ice enabled, so we're getting under ice measurements. And then the data are quality controlled in near real time with static data snapshots every approximately 3 to 4 months, and those have a DOI and are frozen in time. And that's all work that happens at Mbari in Ken Johnson's lab. Next slide. And so there are currently, I went today and pulled this map, there are 164 active SOCOM floats. And so the green ones are reporting data right now, and then the red ones are ones that are under ice or have been active for some amount of time, and they could be lost or they could just be under ice for multiple years. Next slide. So a lot of my initial work with SOCOM was focused on how can we get from the pH to other carbonate system variables. So if you think back to your basic CO2 chemistry, you need 2 of the 4 measurable variables in order to constrain the CO2 system. And so these floats are only measuring pH, which means we need a second parameter in order to estimate the others. So we actually estimate total alkalinity using empirical algorithms that are trained using ship data, and there are several methods out there. But it turns out that the uncertainty in the calculation of PCO2 from a float with a pH sensor, most of the uncertainty in the PCO2 comes from the pH, and the total alkalinity isn't really that critical to get perfectly right. So this works reasonably well. Next slide, please. So in this 2017 manuscript that I mentioned earlier, we did a thorough uncertainty analysis of all the different uncertainties going into getting this PCO2 estimate from a float. And they are relatively uncertain compared to a ship-based direct measurement of surface ocean PCO2. So from a ship, you're going to get about a 1%, plus or minus 1% uncertainty. And from the floats, it's more on the order of 2.7 to 2.8, 2.9. And the reason I sort of am not nailing down a number on that is because this is actually still evolving. So next slide. So there's an OCB pH working group that is going on, and basically the reason this group, one of the reasons this group came about is because there are some uncertainties in the CO2 system itself that are contributing to this uncertainty in PCO2. And for example, this is a figure that's been, this is from my 2017 paper, but Brendan Carter's work has shown a similar thing in 2013 and in 2018, where pH directly measured using spectrophotometry does not match perfectly with a pH calculated from DIC and alkalinity. So there are some uncertainties somewhere in the carbonate system that we aren't fully constraining. And that is going to be really important moving forward in trying to determine the uncertainty in these kinds of sensor-based PCO2 estimates. Next slide. And we've also, I just kind of want to point out that there have been efforts to try to go out and do crossovers with floats, or I guess more accurately, the ships that are deploying the floats oftentimes have an underway PCO2 system on board, but it's not straightforward to compare those underway data with the floats, because the floats typically go down and they don't do their fish profile for about a day after deployment. So you're not really comparing the same water mass exactly. And this past year, we, I should say, Sail Drone and PMEL deployed a sail drone from, was it Tasmania or New Zealand? But it did the Antarctic circumnavigation, and there were some efforts to try to meet up with SOCOM floats and do some comparisons, and it was just really difficult. The sail drone can only go downwind, or that version of the sail drone could only go downwind, and meeting up with something that only surfaces every 10 days is just really difficult. And so we didn't get a lot of great comparisons from that. But overall, the crossovers that we do have with underway data show that the floats are within the uncertainty that I stated earlier. But there may be a slight bias, so about a 4 microatmosphere bias where the floats are measuring higher than the underway system. And as Rick stated earlier, that's pretty significant. So we're still working on beating down these uncertainties. Next slide. And so this is a figure from Allison Gray's paper in 2018, just illustrating that the floats are observing much more outgassing in the Antarctic southern zone, which is shown in that golden orange, relative to the ship-based products. And if you were to use just the SOCOM data to calculate a Southern Ocean CO2 flux, you would get a 0.8 petagrams carbon weaker sink in the period 2014 to 2017. And so that sparked a lot of questions about why do we see this big difference? And I'm not going to try to answer any of those questions, but that's kind of where we're at. So next slide. So Seth Boshinsky late last year published this manuscript along with Peter Landschutzer and others, where they started to incorporate the SOCOM data from that same time period, so 2014 to 2017, into the SOM-FFN neural network. And so they ran it using kind of the traditional, just the ship data. Then they ran it with both ship and SOCOM data, and then with only SOCOM data in the Southern Ocean. And what they found was kind of what we would expect, that the SOCOM data bring the Southern Ocean CO2 sink down. So there's more outgassing or less uptake when you use the SOCOM weighted product. And they also did some experimenting where they looked at what if there is a 4 microatmosphere bias in the float-based PCO2. If you just subtract that from the whole SOCOM data set, what's the effect on the total flux? And what they found was that when you remove that bias, you do get a reduction in the outgassing of about 0.2 petagrams of carbon per year, but that can't account for that full difference of 0.75 that they're seeing. And so I guess I just wanted to I have a couple notes for myself, things I wanted to say, and actually Rick said a lot of them, which isn't surprising considering he's one of my mentors. But I really think it's important what Judith said about terminology. So I think a lot of times we're confusing anthropogenic with non-steady state natural fluxes, and the terminology is just really important, and I'm hoping that we can kind of try to get on the same page with some of those things here. And also that we be consistent. So when we're comparing observation-based products, I think a lot of times people want to just jump straight to comparing the fluxes, and the same with looking at model output. But in reality, there's a lot of uncertainty and a lot of differences in winds and sea surface or sea level pressure products that are used to calculate fluxes. And it might actually be better for us to kind of take a step back to the basics and just compare the PCO2 and or even the DIC and these different data products and models. And I'm excited to see that we're starting to incorporate the SOCOM data into these kinds of estimates, and I hope that we can keep doing that. So I think that's all I have, and I'll take questions.
Thank you, Nancy. Do we have any questions?
Thanks, Nancy. Peter, I just wanted to add something, so it's not really directly a question, but so if anyone is interested in this estimate that includes both SOCAT and SOCOM data, they are also freely available on NCI OCATs. So if you Wojcicki paper, you see that there is a link. So we're not just keep doing that, we also hope that people keep using it. So
yeah, thanks, Peter. And actually, I've been meaning to ask you, have you added the 2019 data yet?
Not yet, but I've seen there was an email by Seth. I've at the moment an inbox that is full, and I think Seth is even might be listening. So I'll read your email and I'll try to do it as quick as I can.
That's exciting. Thank you.
So I'll follow up with a quick question on that. I always wonder about the representativity of the floats in the, if we have a float that surfaces, say, once every 10 days, maybe it catches a 1x1 grid cell once or maybe twice before it gets averaged into a monthly estimate versus a SOCAT data that's probably going to be many tens or hundreds of PCO2 observations averaged into that 1x1 grid cell. So how do we deal with that? What work is being done on that? How do we, because I think that representativity is part of pulling this together, these different approaches together.
Yeah, that's a great question. And I don't think I know the answer, but I do think that these shipboard data sets, while there might be hundreds of thousands of data points in one cruise, a lot of them are correlated. So I think if we can start to bring in satellite data and start to look at, representativity or representativeness of one float profile in certain parts of the ocean, and then obviously put more floats in places where you need more, which, I mean, people are doing that, but I guess that's kind of the way I think about ship data relative to float data.
Ray, did you want to ask your question about total alkalinity error?
Sure. Thanks, Nancy. That's an interesting presentation. And I wanted to know if you're calculating DIC, which I think is probably useful and probably people have done it, especially if you're looking at seasonal variability. It's a thing you want to look at to get budgets and stuff. Is it the same issue that the pH error dominates, or is it different? Is the total alkalinity error become, I don't know, more important when you're calculating the DIC instead of the PCO2?
Yeah, it does actually. The uncertainty in total alkalinity propagates pretty much 1-to-1 micromole per kilogram to DIC. So the uncertainty in the alkalinity estimates is about 4, kind of depending on the product, and so 4 or 5, and so your DIC is going to have that same uncertainty.
And the pH error, what would the pH error be? Calculating DIC.
It's small. I don't remember off the top of my head what the contribution is, but it's actually relatively small. Yeah.
So the total alkalinity error dominates there. Right. Okay. Thanks very much.
Yeah, so that's another kind of important point. I guess that I didn't make was just, so people have been asking, you know, can we put uncertainty estimates on all of these derived products? And the answer is yes, we can, but it depends on what you want to do with the data. So sometimes a systematic bias, or sometimes a random uncertainty isn't really going to matter to you, but a bias would matter a lot, and so we almost need like multiple columns of uncertainty, kind of depending on what you want to do with the data. So,
Right.
yeah, those are things I'm
I have a
thinking about.
question, maybe for Nancy, but also maybe for Adrian if she's on here. I was wondering if you could speak to the near real-time availability of the data that's being produced. For example, one of the things I just talked about briefly earlier was whether you could see the emissions reduction in the ocean carbon sink, and I'm wondering if the data that's coming online now is something that could be used to do that, or if we should maybe talk about that tomorrow.
I think that's a great question. I've been avoiding thinking about that just because I'm overwhelmed, and I've been trying to let people focus resources on things actually related to COVID. But I think, you know, if we have that data, then, and someone has the bandwidth to do it, then that would be a really interesting question. Obviously, there's going to be a lag in the ocean's response, but yeah, those data are mostly good, you know. And there was a snapshot that came out, I would say, I guess it was about 2 weeks ago now. So, yeah, I think it's worth exploring.
And just to clarify, is that snapshot quality controlled in such a way that we could trust it immediately, or do we need to wait for some quality control effort to happen before we can do that? Girls.
No, those snapshots are quality controlled. I mean, they're subject to change in the future. So another snapshot might come out and they might retroactively make changes to those data. But that's the best estimate that we have right now. And I believe that Tanya and Josh have looked at all of those data by eye before they release a snapshot. Yeah.
Great. I have a question related to that on the data. Are the SOCAT observations still coming in, or are there impacts from COVID on the collection of those data? Rick or maybe Dorothy could.
I know for our operations, which is heavily reliant on both the commercial passenger cruise ships, luxury liners, and research ships, our observations have stopped, and they will not resume till the ships start moving, which will be earliest, this summer. Adrian could probably chime in that the moorings and other autonomous sensors are happily continuing as long as they don't have to be serviced and don't break down.
Yeah, this is Adrian. I would just add that the impacts will likely extend beyond this year because, related to buoys, when a buoy servicing is postponed, getting ship time to get back out there again is something that's usually pushed out months and months. So for now, it looks okay. Well, the impacts will likely be next year.
Great, thanks. I think there have been a lot of discussions about the potential impact of COVID on the Earth system as a whole, and I think there is value in looking into this and seeing, maybe perhaps seeing it as a test of our understanding of the mechanisms of the sink to look at the COVID-related reductions in atmospheric growth rate and how it affects the sink. So definitely that's on the docket to discuss tomorrow for sure.
I've got a couple of other questions that have come in. One from Civ Loves It on what is defined as surface for the floats?
Yeah, so the shallowest data point is typically 4 to 6 or 7 meters. And except for if a float is under ice, and in that case, it still samples as close as it can get to the ice, but that tends to be more like 15 to 20 meters, something like that. I'm remembering correctly. Yeah, but I think that's about, I mean, a ship surface measurement, I think, is several meters.
Okay, we have another question from Brian Ward. The operational method for determination of air-sea fluxes requires an estimate of the transfer velocity. I'd like to ask if this working group has a community, which is the direct determination of the flux.
Rick, can you address that one?
Yes. So as I might have been cut out in my presentation this morning, the eddy correlation measurements are spot measurements, and so they are really useful for sort of a mechanistic perspective, but they are very difficult to extrapolate to fill in gaps in that particular way. So and so I think this working group will probably sort of refer to the OCB working group on air-sea interaction, and the SOLAS working groups to get our best information on how we get a better parameterization of air-sea gas transfer. It's something that we will have to be brought up, but it's not, as I view it, the major focus of this GAPS working group. And I think I'm probably the most enthused about gas transfer, so I expect the other members, probably feel the same or less so.
Okay. So there was a question here from Dorothy, I believe. Sorry if I'm misquoting. Maybe I didn't catch all of it, but basically, if we're getting, I think one of the key questions that I think a lot of us have is there's all these different pieces that can bring the observation-based estimates, which we think are a contemporary flux, towards the interior estimates of Gruber et al. That we believe is a more kind of just the anthropogenic change. That's what it's estimating. So is it the rivers? Is it the air-sea flux? Is it aerial coverage of the different products? Is it the marginal seas? Is it the coast? So I think what we really need to do as a working group is try to list out all of those pieces and try to assess where we think the uncertainties are greatest, and what the path forward is with respect to addressing those. Because clearly we can't both have 0.8 in the rivers and 0.7 in the gas transfer velocity and some tens of petagrams in the aerial coverage and other things. So how do we pull those all together? And that, because I think ultimately, and if we believe the interior estimate from Gruber et al., it is a bigger number. If it is 2.6 or is it 2.2, there's also this natural outcasting. There's all these little pieces. But I think one of our first steps probably is just to kind of make pull together maybe just a spreadsheet of all the different potential that pull together the global fluxes and try to hash out where the pieces are that we need to, do the estimates really overlap or not? So does anyone have any thoughts on my ramblings there?
Yeah, Galen, I guess we're sort of talking to each other. But, I think one of the things that I'd like us to think about is that, what, Sabine did was an anthropogenic estimate of the interior ocean since the start of the Industrial Revolution. Nikki and colleagues did the interval from 2007 to 2015. There's nothing that prevents us to get the contemporary change. We don't have to calculate. We want to calculate anthropogenic, but we also can get a contemporary inventory change. And I think that is something that is worth, I have not really gotten a satisfactory answer why we're not doing that. And I think we should look at that, because at that point, we can basically look at contemporary fluxes and contemporary change. They're not at exactly the same time interval, but it will give us some idea of where the issues are. What does that mean, contemporary? Basically, as opposed to when we get Ray, when we get an anthropogenic CO2 flux, we do amazing. I mean, sorry, I'm misspeaking myself when I'm telling people not to. When we get a change in anthropogenic CO2 inventory, we do amazing things. With multilinear regressions, we basically correct for all sort of natural changes. What we should be able to do with our data sets and with good extrapolation is look at the change in DIC in the ocean between time step X and time step Y. So basically, that's one thing I think we should be doing with our GLOAT app and our other database products to see how much that that changes currently without making all these corrections for the answer. And it has a slightly bigger implication as well, because if we look at the big picture,
Rick,
for the ocean, go ahead.
Sorry, just for information, Rick, this is something we've started doing in my group. So really just looking at sort of we'll apply the same methods that we use for the surface mapping to use for the DSC for the interior, and then look at just the contemporary changes in DSC. But this is still ongoing, so I cannot tell you what's
I suppose, though, in that case, the signal to noise ratio is much lower than it is when you do all this correction for just to isolate the anthropogenic CO2, which is probably why that's been done in the past. Whereas if you're just looking at the contemporary changes, then I don't know, you tell me, Peter, but it's going to be, I think, maybe hard to see a signal.
It is, as I said, it's work in progress, but
okay, good luck.
I will, maybe at the next working group meeting I can surprise you, or maybe not. I don't know.
Yeah, that'd be great, though, to have that product looking at just the contemporary DSE inventory change.
Well, this is fantastic. I'm really pleased. But when I was going on in my diatribe, I do think there's an important point is that for some of our questions, it's really the variability and natural change that we're really caring about. If you're looking at trends in ocean acidification, a critter that is susceptible to ocean acidification doesn't care where the acidity comes from. That is basically it's a total change, and there are some other societal problem issue. And the same with anthropogenic CO2 forcing. If we get an outgassing or an ingassing, it's really sort of the result of what the atmospheric levels are, and not necessarily anthropogenic. It's not, I'm not poo-hahing the anthropogenic part and recognize the importance, but there is significant importance to look at the contemporary quote unquote natural change.
Rick, I would argue that these EMLR approaches actually do capture a little bit of the contemporary change, because when you do the fits, including dissolved oxygen, we're assuming that the oxygen is not changing, or that the oxygen relationship with the other parameters is not changing. And in fact, we are seeing a deoxygenation of the oceans, and that will artificially show up as a part of the anthropogenic CO2 signal in the way that it's been calculated. So it's some hybrid in between a true carbon uptake and some contemporary that includes, for example, changes in remineralization that are evidenced from the oxygen changes.
Yeah, and then so I think it brings up the important point is that when we are looking at anthropogenic CO2 inventory changes, we are making significant assumptions and mathematical approaches in order to get those numbers, which we really have to closely look at what's going, what for sort of the physical mechanism behind it.
Yeah, and I guess that also intersects with the uncertainty that's going to be inherent with taking observations that are not truly a snapshot and pulling them together, right? So you're going to always have some uncertainty when you're trying to do 90, a decadal mean from a variable ocean.
Yes, and I think that's an important point you bring up as well, is that I think when we talking about the Gruber snapshot from what 1990, what is 1992 to 2007? I always forget what the correct number is, but it is the average for 2007 was basically cruises from 2002 to 2013, and the same for the starting point. So we are, yes, there is some issues with the way we are averaging, or an uncertainty associated with the way we're averaging, and it's we try to adjust it, but it's still it increases the overall, I think, uncertainty in it.
But in that work, he did try to time correct those to bring them all to a normal year.
Yes, but it is, as you said, he attempted, and I think that I'm sure we all did a good job on it. But we have to recognize that is an added uncertainty, and that we generally do not include in our overall uncertainty estimate.
Yeah, I'd say it's less of an uncertainty though than what we've done in the past, which is just to ignore that time component and average them.
Okay, I'd like to turn to the, we have about 15 minutes left for today, and I'd like to turn to the questions we had at the end of the agenda. I'm on the agenda from the, let's see, they're on the online. They're not on the online agenda. So I don't know if May, if you could put those up on the screen, perhaps. Do you have that handy, the Word doc?
I will open it in just a sec and
thanks.
Checked.
So these questions are just things that Peter and I put together as suggested questions for discussion tomorrow. And I would like to have people look at them and add to this list so that we can make sure we have a good plan for our discussion tomorrow at the working group and then the guests, the panelists here. Okay, so I suppose I'll go over them briefly. What are the critical uncertainties in the observation-based products? Skin effect, gas exchange, interpolation techniques, changing data density, and how can we better constrain these? We can talk about approaches to reduce our uncertainties in those, and obviously the Southern Ocean is a big area, but I think, and obviously increasing data density there is important, but what can we do in the meantime is a question that we can talk about. And I will just, anybody want to add anything here? Or disagree that we should talk about this? I think it's pretty obvious. Okay, going on, pre-industrial river flux challenge for global closure. What's the best approach? One could frame this as what's the number we should use given the current knowledge. 0.45 has been used for a long time. 0.78 is a new number. I think there's a lot to talk about there. The degree to which the new estimates from Robert help us to close that gap or not is something we could discuss. And I think ideally we would have some more independent constraints on this flux. And I think it would be great if we could propose what we would do to come up with the better constraints on this flux. So I would love to have some conversation about that. Any further thoughts on the river flux challenge, as I call it? Okay. So this issue of our open ocean results and our hindcast model simulations, there's many ways to frame this issue. A lot of it is this contemporary versus the anthropogenic flux only and the hindcast models. The issues of course, the river flux, also the aerial coverage of the models. So for example, in IPCC, some of the figures that we're presenting in our group and others, we're just making a correction of the observation-based products that don't cover the full global ocean, particularly the Southern Ocean, and that makes them much more comparable to the hindcast models. So simply because they don't, their area leaves out a lot of the Southern Ocean, you can get many tens of petagrams of adjustment in the database products. If you take into account the fact that the area missing in the observation-based products is actually in the Southern Ocean. So that's that's one thing you can do to bring the mean fluxes closer together. Of course, the river flux is there. There's also this natural outgassing that is was estimated by Gruber et al., but was sort of a back calculation based on the PCO2 products themselves, so a little bit circular. So that's something that could also be brought in there. Comments, Judith? You had something to say?
Yes, I wanted to say on the aerial correction that you applied in the Southern Ocean, just to note that this certainly doesn't hold for all the data products, right?
No.
And particularly not for the ones that they use in the global carbon budget. So I think where the area is really mostly missing is all the marginal seas and the coasts, right? It's the Mediterranean, it's the Arctic, it's the Hudson Bay, it's lots of marginal seas. It's not the Southern Ocean.
It depends on, it certainly depends on what observation-based product you're using. So the Wegener product definitely has full coverage, but the other ones maybe 95% or 85%. So in our paper, we have to make some adjustments up to about 0.3 petagrams of carbon because the Southern Ocean is missing in those products. So, so that's improving over time, but that is an issue that will change the ensemble mean estimate.
It's just dependent on the products, right? It's not the same in all the products.
It is not the same in all the products. That is true. Yes. Yes.
Just a general comment about the river carbon. I don't know if we should be correcting the different models or we can discuss. Of course, people can do whatever they want, but I guess in my view, we shouldn't be correcting the models or the different products for the river fluxes because we don't know what they are. We don't know their spatial distribution. So it seems like the best way to present the different products is just exactly what they predict for the air-sea CO2 flux, and then to explain which processes are included in which of the products. That just seems more straightforward conceptually to me, because I know, at least for myself, I get confused. Oh, this has been corrected, this hasn't been corrected, and in what way the different products have been corrected for that. So it seems more straightforward just to present exactly the air-sea flux that each product predicts and then interpret from there.
I mean, I can agree with that. I think that from a scientific standpoint, I think it makes that would make it just more clear instead of saying air-sea flux and is it contemporary or natural or anthropogenic. But I think in the context of something like the global carbon budget, I don't think that's really an option. So, yeah, go ahead, Judith.
Well, of course, you're right, Tim, and I think that's done in all the individual papers describing their methods and their estimates, right? That they make clear what that is. But if you were to leave it there, you have to refrain from doing any comparison between them. And that's exactly what we want to do.
Well, you could compare, but just say that the discrepancies are due to these various factors, not taken into account in the various products, I guess.
But if this links to this last point here, and so if there's a need for a continuation of this intercomparison, and what should this intercomparison include? I mean, I think this could also be sort of a chance to make it sort of start a protocol and say, like, look, when you create or when you update your methods, please make sure that what are the important what the important factors to include. For example, make sure that you all have the same area. Maybe only 80% or 88% of the global ocean, but at least it's consistent. To make a comparison and have it as a baseline, or or sort of have it as a protocol that there is the time frame has to be the same, or that uncertainties have to be estimated by sort of a common protocol. So is there a need sort of also to unify that? And maybe Christian has got some thoughts on that, as he's actually leading this SOCOM intercomparison.
I think there are
always pros and cons in in unifying things. So if you unify, then the intercomparison gets easier. But on the other hand, you lose probably possible ways to do things, and you lose part of the uncertainty also. So it's something which needs to be thought through carefully, I would say.
Yeah, I think that certainly this working group can make progress in identifying some of the key issues that should be considered and that need to be discussed based on what we've learned so far. I also think it was Nancy who said that she felt like we really should be comparing PCO2 across these approaches, which I totally agree with, and that's definitely been something I've always struggled with in publishing papers, because I want to talk about PCO2, but the reviewers really seem to care more about CO2 flux. So in our recent paper, I'll just make one comment that we recently were trying to compare PCO2 from the global carbon budget models and the products, and found some really strange things. And we realized it's because the water vapor correction was not being applied in most of the global carbon budget models. So the PCO2 is actually not comparable to the observation-based products. And so we had to make some assumptions and make a correction on the PCO2 from the models in order to be able to directly compare it to the observation-based products. So also on the modeling side, there's some things that we could say that might help increase the intercomparability. And it's some things that are relatively, I mean, I'm sure Rick Wanninkhof is not happy with the fact that the models don't include the water vapor correction based on reviews to my papers you gave me long ago, Rick. But yeah, so I think there are some very basic things out there that could be laid out that would help.
One question of interest, Gabe, did this water vapor correction, applying that one, did it improve the comparison then?
Yeah, much improved. So we found that a much smaller delta PCO2 than what appeared without that. And it's very similar to the observation-based products, yes.
But it probably didn't change the flux, right?
No, the flux didn't change at all, because the models have adjusted to a time history of PCO2 that is just slightly higher. So this didn't change the flux at all. But you're getting this weird, why is the delta PCO2 bigger, but the flux is, not significantly bigger, and that's why.
Because the circulation is what's regulating the uptake. And so, in some ways, given that, it may make more sense to compare fluxes than it is for PCO2.
You would think it would be 6 of one and half dozen of the other, except for the winds and these other things that we know about. You'd think it would be easier, but there's a lot of things that come up that you don't realize. But I think if we want to go with PCO2, then we need to try to get the models to present a PCO2 that's more comparable to the observed. That would be a suggestion I would put out there for the modeling.
Agreed.
I guess another for the community, the global carbon community, to use fluxes is then you can also compare to atmospheric inversion, which only get the flux and not the PCO2, I guess.
Yeah, I agree with that, and that's why we talk about flux. But I think maybe as ocean carbon cycle scientists, maybe if we could learn more if we focused on PCO2 for a while, but then we have to resolve some of these issues, I guess is the point.
Yeah, and I absolutely agree that the model should include that. Just for clarification, I think it's even worse than just the water vapor correction. I think what it is really the conversion from XCO2 to PCO2, which includes the atmospheric pressure and the water vapor correction. And just calling it water vapor correction makes the problem actually look smaller than it actually is. But I do think it's roughly half of the models that do it in the global carbon budget now, and the other half not. But yes, I strongly support the recommendation to include that. And I think it's coming. I think there's new model code out there, right? I think there's a history to that. In the old OCMIP code, it was not in there, or it was part of the forcing. I don't know what happened at that time. But as people move to a newer code where that's intrinsically included, we get out of that issue. It's not a big thing to do, but yes, it needs to be done.
To address, Ray's point, which is an important point, that in general circulation models, it's not the air-sea gas exchange which is restricting uptake, and so these things do fall out. But you do have this. You will see significant, even if not in global effect, you will see significant differences on regional areas because both the water vapor and the pressure correction, which Judith has mentioned, have a very strong latitudinal gradient to it, or temperature-based gradient, and so that you will see quite a different efflux in the equatorial Pacific versus uptake in Southern Ocean, depending what you use. And like I say, it all averages out, but it is when we want to get a better process understanding, I do think it's worth including, which everybody seems to agree with.
Yeah.
I'd like to say something, just go back to a previous bullet about the pre-industrial river flux. I mean, my looking at the literature on this, sort of the bottom up approach, and Laura sounds like she's done some update on this. So there may be more to add, but my sense is that that the biggest uncertainty is associated with the burial number, and that's what you need. It's a difference between the riverine flux and the burial, basically, is what it's going to give you this sort of natural outgassing. And while the riverine one is known fairly well, the burial seems to me, as my looking at the literature, is there's quite a bit of variability. A lot of that burial is happening in shelves. And there may be a fair bit happening in estuaries that we really haven't accounted for. But just the shelf estimates that I looked at, as I pointed out in my talk, varied from many tenths of a petagram of carbon. I have to go back and look at that. So, we may have been overconfident about what that number has been. And then we need to be careful, as I pointed out before, is to not conflate that with the interhemispheric transport, which is a different number.
So then, Ray, that leads perhaps a nice segue to the coastal ocean discussion questions, where we started off with, is PCO2 enough? I mean, if you really could blanket the ocean and know the PCO2, in theory, the burial would be captured in that, right? But it's, of course, we don't have enough data. So you're saying
the burial would be captured in it. You would still have to, do this river loop correction, right? I'm not sure what you meant by the burial captured in that.
Well, I mean, if we could know exactly the PCO2 everywhere in the coastal zone, I guess we could know how much exchange is happening there. But what you're saying is, if you don't know the burial, you don't know how much is being flushed through the coastal zone to the open ocean and to be redistributed in the global ocean, like in the OMIP estimates. Is that that's the point?
And some of it is maybe, this river stuff is actually coming out in estuaries. There's definitely a lot of CO2 coming out of estuaries, and that's not it's not fully accounted for. I mean, it's present in some budgets, but a lot of what we saw today was not present.
And when you said you felt like the river is known okay, you're saying the stuff that is coming from the river into the estuary, so above the estuaries, right, above that. And so,
right. I mean, the number hasn't changed since Maybeck's great work in the 80s. It's 1 petagram, and people keep rehashing it. And I don't know if this is the priority of the paradigm, where you always try to agree with what people have done before. But boy, you haven't really seen that number shake very much. Mm-hmm. So, I mean, it could be that there are issues with it associated with, the way these fluxes are calculated is pretty simple. You take a stream flow and you multiply it by a mean concentration, and seems to me there's some effort to account for covariation, but maybe there's still wiggle room there. And then, but the burial one is where I my sense of the literature is where the real
Ray?
uncertainties
Can I,
lie.
can I,
Were your headphones connected by a USB or something, or how are you?
Ray, can I say something?
Plugged it
Please.
in.
Laura, go ahead. We had some side conversation going on there somehow. Laura, we can't hear you if you're talking. You're muted.
Yeah, sorry about that. I was saying so there is a nice new estimate of POC burial that is coming out soon by Sandra Arndt. So I hope that it's a very nice study, and it's over the whole Holocene, like sediments, and so I hope that will address some of those concerns that you were talking about, Ray. For the PIC, it's a different story, but for the POC, at least, I think it's a nice new product that will come out very soon.
That's great.
Yeah, just okay.
Go ahead, Tim. Yeah, please.
Oh, I was just going to add to what Ray was saying. And I think maybe it's the organic carbon burial that matters more than the inorganic carbon if the kind of alkalinity is in balance. But the another point for the kind of coastal ocean is the carbon that's fixed kind of in coastal ecosystems and then exported to the ocean. That's probably not included in those kind of top-down river discharge-based estimates of the carbon that's coming in. Could be another point to think about for the coastal ocean is how much carbon is being fixed in that region, organic carbon, and then exported to the open ocean.
Okay, we've got just a couple minutes over here. We're going to talk tomorrow also about integrating open ocean and coastal ocean.
There's one question, Galen.
Mhm.
Flux question, if you wanted to take a peek at it. Regarding riverine flux estimates, how this should be partitioned between DIC and DOC riverine inputs and ocean models. Is there any conventional approach? That was the last one that came in.
Yeah, okay, as I am, maybe Nikki Lovenduski or someone else has or Judith maybe, but most of the global models of which I am aware do not do DIC and DOC going in from the rivers. So I don't think there's a conventional approach, but maybe someone else who's more familiar can say.
I also don't think there's a conventional approach. And I put in the chat at some point, although it's hard for me to find it, a response to Ray's question from perhaps this morning that describes the OMIP protocol for river input, just to give you a sense of how confusing it can be, and how different modeling centers can do basically whatever they want in that. So there's no consistency in the approach from what I can tell.
I think most of if models do include that, most of them probably still go back to the Ludwig paper from '96, which would give 0.2 gigaton carbon in dissolved form and 0.17 in particulate form, but totally not up to date whether that's exactly what all models do.
Talking just about organic carbon, Judith.
No, so the first was inorganic, right? Oh no, hang on. Yeah, that was just the organic. That's right. But then, I mean, there is, yeah, I would need to check. I'm not sure either. But there's also, I think most models also add inorganic. That's right.
Okay, so the other topic that we were going to talk about, going back to the open ocean that I didn't rehash here, was the potential to think about what's happening with COVID. Are there any interesting things that we should be doing or trying to say about that with the cuts in emissions and the potential impact on the ocean sink? That is, we're about 5 minutes over time. We've gotten through our agenda pretty well. I think we're ready to close it out for the day, but do any people have any additional comments or questions before we say goodbye and thank you to everyone? Okay, no final questions in the Q&A. Okay, well, thanks everybody so much for being here. Thanks to OCB for facilitating the WebEx. We really, I think it was great. Thanks everyone to keeping on time, of course. I look forward to the conversation tomorrow with the working group and to ongoing conversations with everybody on the meeting here. So thanks to everybody. Have a good evening. Stay safe and healthy, and look forward to seeing you again soon. Okay.
Thank you. See you tomorrow.
Thank you, everybody.
Thank you, Gail.